You can find it in the rainforest, on the frontiers of medical research, in the movies, and it's all over the world of wireless communications. One of nature's biggest design secrets has finally been revealed.
My God, of course, it's obvious.
It's an odd-looking shape you may never have heard of, but it's everywhere around you. The jagged, repeating form called a fractal.
They're all over in biology. They're solutions that natural selection has come up with over and over and over again.
Fractals are in our lungs, kidneys, and blood vessels.
Flowers, plants, weather systems, the rhythms of the heart, the very essences of life.
Okay, the topic I'm going to introduce today is the topic in mathematics of fractal geometry. Up until now, our mathematics has consisted of essentially the calculus. And calculus, as we're going to find out, is great and really perfectly suited for defining man-made things. But as we're soon going to see, nature operates on this principle of fractal geometry. And so we're going to see that everything from the pattern of your heart, of a healthy heartbeat, to the arterial branching in your body, weather systems, even the surface of the moon, tree branching, and our coastline are all defined in terms of a fractal. Okay, now I'm going to show how a fractal has a non-integer dimension. Okay, we'll start with a very simple fractal. We'll just take a straight line. And I'll take this line and I'm going to divide it into 3 equal length segments. Okay, well, if you will here. Now if I take these 2 end segments and attach 2 segments that converge, and I make these 2 segments each the same length as this original segment, I now have this line. I now have what is known as the Koch curve, and each segment is 1/3 the length of the original segment. So if I use the formula that we've derived, n is equal to the scale raised to the dimension, we now know that the dimension is equal to the log of n over the log of the scale. We know that in terms of the Koch curve, to calculate this dimension, we have the log of the 4 pieces divided by the log of the scale, which is 1/3, which is each piece is 1/3 the length of the original segment, so forth. So therefore, it's 3:1, and this equals approximately 1.26 or 262. We can round it off. And here you can see right away that this curve has a non-integer dimension. And those are the 2 components that make up a fractal. As you can see here, we've got the simple fractal in action, the Koch curve. I've taken a straight line, broken it up into 3 equal segments, erased the middle segment, and attached 2 line segments that are each 1/3 as well of the original length. So now I have 4 segments, each 1/3 of the original length. So now I have a length which is actually 4/3 the original length. So the curve, as you can see, it's going to produce an infinite length because each time the steps above are performed on each line segment, there are 4 times as many line segments. The length of each being 1/3 is the length of the segments of the previous stage. So here, what I've done here essentially is I've created a triangle out of each one of these lines, an equilateral triangle. Down here, I've broken up each one of these sides into one of these curves. So as you can see, this is the first iteration, this is the second. In the first, you produce 1, 2, 3 triangles. In each subsequent iteration, you produce 4. Okay, so you can see the Koch curve is continuous everywhere, differentiable nowhere. Okay, taking S as the length of the side, the original triangle, by formula. The equilateral triangle, which you can deduce, is s squared rad 3 over 4. And the area of each triangle added in the nth step is 1/9 that of the n minus 1th step. So here you have the first iteration, called a sub n and a sub 1. If I work this all out, as you can see, I've worked through the steps. The original area plus, since the area is 1/3, is the square, is proportional to the square of the n minus 1th step in the first iteration. The area will be of a sub 1 will be 1/9 the previous area. If you work it all out, you end up with a sub 1 is equal to s squared rad 3 over 3, or a sub 1 is 4/3 a sub 0. Okay, now what I've done here is I've taken, as you can see, that original first iteration, which we calculated as 4/3 of a sub 0, which would be this first iteration here, and I've added a sum from my second iteration on up to n, which would be our subsequent sums of our areas added to our original area, which would produce an area of n plus 1. For the first iteration, we have this. For the second iteration, we would produce, like I said, the first iteration produces three extra triangles. The subsequent iterations will produce consistently 4 triangles. So for my second iteration, you can see right away I would have 3 times 4, or 12 triangles. And since the area is proportional to the square of the side, each area being 1/9 of the n minus 1th iteration, I would have to take 1/9 to the k. So for my second iteration, it would be 1/9 of 1/9 of the original area, because the areas of these triangles, of course, are 1/9 of this area. These smaller 12 triangles are 1/9 of this one, which is 1/9 of that one. So it would be 1/9 to the k. And we would sum these, and we would end up with the following iteration. So a to the n plus 1. As you can see, you work out these calculations. Here in this second step, what I've done is multiplied by 3 and divided by 3, so that I can create a coinciding geometric sequence or series. If I do that, as you can see by the math, I'll end up with 4 over 9 to the k, and you can see that this is a convergent geometric series. And from our second semester calculus, you know if 0 is less than or equal to the absolute value of r being 4/9, and if r is less than 1, if it is within this interval, it is within an interval of convergence. And by a simple formula of a over 1 minus r, we would calculate, if our index were 0, that this would in fact actually be 9/5. But since we're starting at 1, we would have to subtract 4/9 to the 0, which is 1, which would be 5/5 from 9/5, and we end up with 4/5 as our converging sum from 1 to n. And if we calculate all this, multiply and add it together, we end up with our limit of our sum of our areas being 2 times s squared rad 3 over 5. So you can see that the area of this fractal is converging to a finite sum, and at the same time the perimeter is expanding infinitely, because each subsequent iteration creates a perimeter that is 4/3 its previous, by virtue of the fact that you're breaking up your lines, your sides, into 4/3 your previous length. So it's consistently 4/3 of 4/3 of 4/3 greater than its previous iteration. But you can see right away that the perimeter is expanding infinitely and the sum is converging. So these are some of the characteristics of a fractal.